Welcome to next lecture of this course, Psychometry of Air. Introduction to psychometry and properties of dry air. Dry air is, there is no water molecules in it. Psychometry is the branch of thermodynamics that deals with thermodynamic properties such as air-water mixture, commonly referred to as moist air. Air-water vapor mixture. For example, we talk in terms of relative humidity. Today, the relative humidity is very high, 80%, 90%. In North India, June, July, August or July, August, you will have very high relative humidity. That means to say, there is lot of water in the air. When there is lot of water in the air, what will happen is you will always try to have a sticky nature, because the water from your body will try to come out. The external also has lot of water, so the water cannot get out of your body by drying phenomena, so it gets stick there. So, relative humidity, when we talk about, we always try to take the property from air-water vapor mixture. It is this property, air-water vapor mixture, is very important when we try to use in the field of HVAC. HVAC is used in all malls. Wherever you have an air condition, we always call this system as HVAC, heating, ventilation and air conditioning. When you go to any mall, you see inside the mall there is always cool air, cool breeze, or you find a comfortable temperature there. It is because of this HVAC system. So, this property of psychometry is very important for in the field of HVAC. Then meteorology, dry processing and refrigeration system. The dry component of air behaves approximately as an ideal gas, and its thermodynamic behavior forms the basis for the analysis of humid air. So, there are two things I said, air, water vapor. So, when the air is completely dry, so what happens is the rest whatever left is water vapor. So, when the air is dry, it is approximated to ideal gas. The goal of psychometry is to understand the behavior of moist air as it undergoes various processes such as heating, cooling, humidification and dehumidification. Humidification is you try to pump air into the atmosphere is humidification. You increase. When do we do this? In dry atmosphere, or when you are trying to sleep in a cold winter day. What happens is you put a heater and then you sleep. When you do so, what happens? The room air, whatever it is, becomes very dry. So, that is why in a corner of the room we try to fill in some water and keep it. So, the water tries to add water vapor into the atmosphere or into the room. So, that is called as humidification. Dehumidification is I try to extract water vapor in the air. So, that is dehumidification. So, we use this in the air conditioning system. So, psychometric chart is very important to understand the moist air behavior. So, psychometric is a study of the thermodynamic property of moist air, specifically mixture of dry and water vapor. So, if you see here, atmospheric air has a mixture of permanent gases, nitrogen, oxygen, argon, hydrogen, etc., etc., etc. You will have water vapor also inside, and you will have dust particle fumes also there. These are all part of atmospheric air. So, after you put a filter, you try to take in the filter what happens? You remove the dust, and then this only enters into the system. That is why if you see in our air condition, whatever we use in our house, let it be a split AC or a window AC, it frequently requires cleaning of filter, because the filter removes the dust particles and the rest enters into your system. So, then what we do is we try to remove the moist air, or the moist air for conditioning, we also try to take it inside and go into the system. So, it focuses on understanding how these properties like temperature, humidity, enthalpy interact with the change of various process. What are the process? Heating, cooling, then you can say humidifying and then dehumidifying. This is what happens inside the room. So, now friends, you see how important is this psychrometric of air. Dry air. Dry air, as I told you, so there are two components. No? One is air, dry air, then it is another one is water vapor. Two components, right. So, now if I can try to make one understand properly, so whatever is the balance will be water vapor. So, then it can, for example, it can be like for 50% of dry air plus dash is equal to 100% of whatever air. So, now if I know one property thoroughly, then I know the end value, I can just subtract it and get this x. So, again and again we are trying to emphasize, let me understand this dry air more. So, dry air is assumed to be a mixture of gases, mostly of nitrogen and oxygen, that behaves like an ideal gas under atmospheric condition. So, it obeys the ideal gas. What are the properties? It is PV equal to nRT, which is an ideal gas law, or PV equal to RT. So, what we did is we converted this V divided by N. So, it became small v, where P is the pressure, V is the specific volume, R is the specific gas constant, and T is the temperature. So, the dry air contains no water vapor and its properties are used as a reference when studying the moist air. Just for a simple calculation, we understand more and more of dry air. Dry air is equal to ideal gas is equal to PV equal to nRT. Now, specific heat of dry air. The specific heat capacity at a constant pressure Cp and a constant volume Cv for a dry air can be found out to be this. So, Cp takes a value of 1.005 kilojoule per kg K, and Cv tries to take kg kilojoule per kg K, specific pressure and specific volume. So, when we try to take a ratio between Cp and Cv, you always try to get a gamma value of 1.4. That is why in adiabatic we always try to take a gamma 1.4, right. So, in this ideal gas, so this is what it is. Friends, you do not have to memorize these units, whatever the magnitude, you do not have to worry about. In the examination, I will give you what is Cp, what is Cv. These values are essential for calculating energy change when dry air is heated or compressed. Enthalpy and internal energy of a dry air. For an ideal gas, I know the specific internal energy and enthalpy of a dry air, which depends on the temperature. So, U equal to Cv constant volume temperature and H is equal to constant pressure temperature. So, the changes in enthalpy and internal energy, enthalpy is H, internal energy is U. Changes in internal energy delta U, change in enthalpy delta H. This can be figured out by this formula. Cv is Cv T2 minus T1 or Cp T2 minus T1. So, these formulas are crucial in heating or cooling calculations. The density of air is the rho component. What is density? Mass by volume, right. Using the ideal gas equation, rho equal to PRT, where rho is the density of air, and at standard condition 1 atmosphere, the rho is nothing but 1.18 kg per meter cube. This is what I wrote, mass per volume. So, till now what did we see, friends? I will just rebrush. We in a psychrometric chart, we saw about dry air, because in psychrometric chart you will have two things, one is air, the other one is vapor. So, we are trying to understand air. So, dry air, we try to convert this dry air into an ideal gas. We saw the ideal gas equation, then specific heat of dry air we saw, gamma we defined, and then we saw the change in enthalpy and internal energy for dry air. Finally, we saw the density also. Now, when we try to see a dry bulb experiment and wet bulb experiments, these are the experiments or dry bulb and wet bulb temperatures we use. So, dry bulb thermometer. So, there are two thermometers, one is called as a dry bulb, the other one is called as the wet bulb thermometer. So, here what do we do is we put a normal thermometer, right, and it is called as dry bulb thermometer. We pass hot air or air from the heat from the atmosphere. For example, take it like a normal thermometer, put it in your mouth, you have a raised temperature, there is mercury there, this mercury keeps rising. And here you have graduations, you can try to figure out what is the value. So, this is for dry. Right. Now, let us go for wet. The only difference between dry and wet is here also you blow heat air, but in wet what we do is we cover it up with a wet cloth. So, when we cover it up with a wet cloth, the heat which falls on it is used to evaporate the water content in the cloth or whatever you cover it. So, the heat used for vaporization of water to atmospheric air is done here. So, here what we do is this is what is the dry bulb temperature. So, dry bulb temperature comes up to here, the wet bulb temperature comes up to here. So, this difference is called as wet bulb depression. Dry bulb, wet bulb, dry bulb thermometer, wet bulb thermometer. The difference is you try to cover it up with a wet cloth. Note, if atmospheric air is saturated, then vaporization wouldn't take place, because you try to pass heat. Here it is a wet cloth. Now, it is there in the atmosphere or already enough of water is there, then the vaporization cannot happen. That is what we say. If atmospheric air is saturated, then vaporization wouldn't take place. So, whole of the heat will be transferred to the wet bulb. So, in the case of saturated air, the dry bulb temperature is equal to wet bulb temperature. For dry air, the wet bulb will be maximum. For saturated air, the wet bulb will be 0. So, this is important. For dry air, wet bulb will be maximum. For saturated air, the wet bulb will be 0. So, the moist air as a mixture, moist air is nothing but dry air plus water vapor. While dry air behaves like an ideal gas, the water vapor content greatly influences the air conditioning and the meteorological calculations. The water vapor. The total pressure of the moist air is the sum of total is nothing but a sum of dry plus vapor. Partial pressure, which is according to Dalton's law, we try to get it. P total is equal to P of pressure, dry air pressure, and P vapor pressure. So, this is the foundational to understand relative humidity, dew point and other psychometric properties. I have now introduced a new terminology called as dew point. Relative humidity is what we see every day, which is getting reported. In psychrometry, humidity describes the amount of water vapor present in air. Since air can hold varying amount of moisture depending on the temperature and pressure, several terms and definitions are used to quantify the vapor content accurately. So, moisture depending on the temperature. So, this is very important. In air, holding. So, what does it mean is you can have RH 60, relative humidity 60 for a temperature of 30 degrees Celsius, for a temperature of 40 degrees Celsius, or for a temperature of 48 degrees Celsius, no problem. Relative humidity constant. Or you can say as and when the temperature goes high, the relative humidity goes low. Or you can try to have the temperature is 25 degrees with RH as 90, then you can have T is equal to 30 degree where RH is still 90 you can have, possible. So, that is what they say. Since air can hold varying amount of mixture, so 90, 60, depending on the temperature and this temperature in turn in pressure, several terms and definitions are used to quantify this vapor content accurately. So, these parameters are essential for understanding human comfort, designing HVAC systems, drying material and conducting meteorological studies. Drying material is, for example, solar drying you do, room temperature drying you do. When you try to take a cloth, you wash a cloth, you put it in a sunny day, you put it in the string, it gets dried within an hour, right. The temperature is very high, air does not have any water content, vaporization quick. Try to do it on a rainy day where the temperature is still 30 degrees Celsius, you wash and put the same cloth on a string, you can see that it takes a long time to go because there is water content in the atmosphere. Second thing, let us look at drying of vegetables. See, when my grandmother was there, she used to make papad, and this papad used to be made at room temperature, and then she will go to the terrace and leave it for drying. And this episode will happen only during on a sunny day or on summer. Or you take potato, you try to slice potato, then you bake potato, and then you make chips, you dry it in the air. So, now the question comes is, how will it dry? What will be the time to taken for drying? So, this looks to be little crude. Now, let us move towards the fast moving segment industry. You buy potato chips. You buy potato chips. Now, the chips whatever you buy, it cannot get burnt more, it cannot be burnt less, and the chip has to warp and it has to make a shape. It is not expected to be flat, and then on top of a chip you have serrations. Now, you see it is the surface area increase. Now, you put it in oil where the temperature is high, the chips becomes crispy and it tries to take a shape. So, now there are industries which work on drying material. How do I play with pressure, temperature and time and get the drying done very fast or cooking done very fast? So, this is very, very important. Domino's Pizza uses this. If you go to Kentucky Chicken, they use this. They try to understand psychrometry of air. They understand this. That is why what they do is their machine is always made in such a way it does not get disturbed because of the environmental factors. The environmental factors are this RH and T, right. So, it is very important. The key humidity term include absolute humidity, specific humidity, relative humidity and humidity ratio. Each describes the moisture content from a different perspective. Let us first understand about these in more. Fog occurs when air is saturated. I leave this question to you. Why? Think about it and try to find out an answer. This is a question for you. Think and then solve. This answer is there in the previous slides what we discussed. Absolute humidity, which is called as AH. Absolute humidity is defined as the mass of water vapor per unit volume of moist air. It is typically expressed in kgs of vapor per cubic meter of air. This is what is the formula. It is typically expressed in kg of vapor per cubic volume of air, where mv is the mass of water vapor, v is the volume of air vapor mixture. So, we try to calculate AH. Absolute humidity is defined as the mass of water vapor per unit volume of air is absolute humidity. Specific humidity, there are several terminologies AH, SH, RH, right. SH is specific humidity. Specific humidity is the mass of water vapor per unit mass of moist air, which including both dry air and vapor. So, it can be expressed as, see the previous one was mv by v. Here we try to express it as mv divided by ma plus mv. mv is the mass of water vapor, ma is the mass of dry air and mv Here plus mv is the mass of the water vapor. So, this is called as specific humidity. In HVAC, in ACs and in dry calculations, specific humidity is useful, but less common than humidity ratio is used, but it is less common than this. Typically, it ranges from SH ranges from 0.005 to 0.030 kg. Next, humidity ratio. Humidity ratio is also called as mixing ratio. The most commonly used measure in engineering application is the humidity ratio, which is the mass of the water vapor per unit mass of dry air is mixing ratio. Using the ideal gas law and Dalton's law, this can be written in this form, where the humidity ratio is 0.622 times PV divided by P minus PV. What is PV? PV is the partial pressure of water vapor and P is the total atmospheric pressure. And this is a constant. 0.622 is the ratio of gas constant which we take from ideal gas, and Dalton equation we put and then we try to get it. So, humidity ratio or mixing ratio is a very important parameter. Friends, you see this example here. Now, you will try to understand what is this, and then you will try to see what is its relevance towards mixing ratio. There is a sponge, somebody is pressing it, the water drops. Last humidity is the relative humidity. Relative humidity is expressed as the degree of saturation of air with moisture and is the most commonly reported humidity metrics in weather forecast and indoor air quality measurements. RH is relative. So, we saw what is absolute humidity, we saw specific humidity, then we saw humidity ratio or mixing ratio, then the last one is relative humidity. This is most commonly used because it tries to talk about the degree of saturation of air. So, relative humidity is phi, which is PV divided by P saturation at a given temperature, air temperature into 100. So, PV is the partial pressure which we have already written here. PV is the partial pressure of water vapor. Here also it is the same. PV is the actual partial pressure of water vapor. P saturation is the saturation vapor pressure at a temperature T. Then RH can range from 0 to 100%. Extremely dry air on a very hot summer or in desert region, hot, where there is no possibility of vapor, you can have it as 0 degrees. But the other way around, 100 degrees is June, July, in August. So, that is why we always say in North India, July, August, because what happens, the rain is also there, the temperature is there, the air is stagnant, air cannot move, right. So, in North India what happens, you have Himalayas which is stopping the air movement. So, the air gets completely hit and then saturated. So, Delhi, Kanpur, you go down to Bihar, then you go down to Chandigarh, Punjab. So, everywhere what happens, there is a stop of air. So, there is no air movement. So, whatever was the air, it is still existing air. So, that has lot of water content because it is raining, and the river also evaporates because of the temperature, that also gets into the atmosphere. So, the RH can go up to 100%. So, that is called as completely saturated air. You can have dry air, you can have saturated air. Now, what happens is, when we try to plan a HVAC system or a AC, we try to see the relative humidity and plan it accordingly. So, friends, there comes a question to you. Why are we not planning to have RH also set in the AC? AC, what do? You always set the temperature, 18 degrees, 24 degrees, 26 degrees, you set a temperature and then you sleep. So, when depending upon the RH, why do not we also change the RH setting of the system and then you start sleeping? So, then you will have a better control, isn't it? But there is no option. You please think about it, why there is no option. high relative humidity means the air is close to saturation and cannot absorb much more moisture, which affects the comfort and drying rate. So, next definition in this is dew point temperature. Dew point temperature is the temperature at which moist air becomes saturated when cooled at constant pressure. Dew point. Dew point is a temperature at which moist air becomes saturated 100% when cooled at constant pressure. At this point, condensation begins. So, I will give you a situation where exactly it happens. You have a closed room, right? In a closed room, you have the RH as 100%. Then this room is at atmospheric pressure. Now, in this room, if you try to have an AC which is maintaining a temperature of 22 degrees Celsius, and if you have a glass plate there or a glass window there, then you can see that there is precipitation of water. So, when the precipitation happens, it is nothing but condensation begins. Now, that is what is dew point. Dew point is a temperature at which the moist air becomes saturated when cooled at constant pressure. Dew point is a critical indicator of atmospheric moisture and is calculated using empirical charts and equations relating to partial pressure. PV is equal to Psat multiplied by temperature into, that temperature is nothing but dew point. Dew point is always less than or equal to the actual air temperature. Keep this in mind, very important point. The dew point is always less than or equal to actual air temperature. The next discussion will be degree of saturation. So, we saw the degree of saturation here also, degree of saturation of air in RH. So, degree of saturation is defined by mu. Degree of saturation, which is denoted by a Greek letter mu, quantifies how close the air vapor mixture is to begin fully saturated with water vapor at a given temperature and pressure. How close the air vapor mixture is to begin fully saturated with water vapor at a given temperature and pressure. It is defined as a ratio of actual humidity ratio W, which is the mass of water vapor per unit mass of dry air, to the humidity ratio at the saturation Ws. So, it is defined as W is defined as mass of the water vapor per unit mass of dry air to the humidity ratio at saturation Ws, which represents the maximum amount of water vapor the air can hold under the same temperature and pressure conditions. This is a unitless parameter, it is a ratio. So, it is a unitless parameter and always takes a value less than or equal to 1. With a value of 1, it is fully saturated. It takes a value between 0 to 1. So, it says less than or equal to 1, right. With a value 1 indicates means it is fully saturated. So, the equation for this can be mathematically expressed in this form. This is extrapolated from the previous whatever we have seen. So, mu is nothing but W by Ws. Mu is okay. So, I will write it mu is equal to W by saturation. So, that is what we told here, na? Which is the mass of the water vapor per unit mass of dry air to the humidity ratio of saturation at Ws, right. So, this at a temperature, at a pressure, at a given temperature and pressure, it can be represented as partial PV by PS 1 minus PS by PV by PV by PT. So, it can be this can be expressed and then it gets converted into this. So, here PV is the partial pressure of water vapor, PS is the saturation pressure of water vapor at a given temperature, PT is the total pressure of air vapor mixture. So, it is expressed mu is equal to W by Ws at a known pressure and temperature. It is represented as PV by PS, which multiplied by 1 minus PS by PT divided by 1 minus PV by PT. Okay. The symbol phi denotes the relative humidity, which is related but not identical to the degree of saturation. Now, let us try to look into psychrometric chart. Psychrometric chart is a graphical representation of thermodynamic properties of moist air at constant pressure, typically at 1 atmosphere. So, you have this chart. So, here you have enthalpy. So, you have and then here you have absolute humidity, then you have bulb temperature here given. So, these are two things, saturation line. So, then you have this enthalpy, bulb temperature, which is normal room temperature, absolute humidity, which is this. It is a powerful engineering tool used in HVAC, meteorology, drying and various industrial applications to analyze the air conditioning and humidity related process. By interpreting this chart, one can determine the state of moist air and analyze transformations such as sensible heating, cooling, humidification, dehumidification and evaporative cooling. So, that is why this chart is very, very important. This chart is very simple. It talks about known parameters P and T, which is measurable, and then it tries to talk about internal energy, enthalpy and entropy. To some extent you can try to get it, and then what happens, it has a specific volume. This is all there, right. So, now you have what are the saturated temperature, you have above and below, right. So, that is what is put here. So, once you know this, then you can try to plan a system where you can enjoy staying inside a room. So, the horizontal axis is dry bulb temperature TDB, dry bulb temperature in Celsius. The vertical axis is humidity ratio omega in kgs of water vapor to this. So, then you have dry bulb. So, this is dry bulb temperature in the horizontal axis. Vertical axis you will have humidity, and then you will have saturation curves. So, this saturation curve talks about 100%, 80%, 60, 40, 20, and you can try to find out the relative humidity line phi relative humidity curve, and then you have relative humidity line you can try to have. These are saturated curves, 100, 80, 60, 40, 20, you can have x and y axis are given. So, horizontal axis is dry and vertical axis is specific humidity. So, represents the actual air temperature measured with a standard thermometer, which is there, dry bulb, you remember. Humidity ratio, it indicates the amount of water vapor in moist air. Then the saturation curve up to 100% is there. All points on the line represents the saturated air under relative humidity phi equal to 100. So, the RH relative humidity line, RH, the curved lines from bottom left to top right. So, here we try to have 10%, 30%, 60%. So, it is constant relative. So, you can try to have this. Right. The next is wet bulb temperature line WBT, which is diagonal slope towards the left, indicates the lowest temperature air can reach through evaporative cooling at a constant enthalpy. Then you have enthalpy lines, which is nearly parallel to the WBT, wet bulb temperature, which shows the total heat content sensible and latent of moist air per unit kg of dry air. So, it is given in this. So, you can see here enthalpy is given here, constant wet bulb temperature lines are here. These are wet bulb lines. So, a specific humidity you try to draw with 15 degrees, 10 degrees Celsius, 5 degrees Celsius, and this is the dry bulb temperature. So, the specific volume lines can be done. These lines are nearly horizontal, wherein which you can try to see the dew point temperature 5 degrees, 10 degrees and 15 degrees and 25 degrees shows the volume of moist air per unit mass of dry air. You try to calculate this. Then dew point temperature. Dew point temperature is located by projecting horizontally from the state point to a saturation curve. So, this is a saturation curve. So, what you do is from the state point you project lines, right. So, indicating the temperature at which condensation begins if air is cooled. So, this is a specific volume you try to hit here, bulb temperature you try to hit here, then moisture you try to hit here. So, now what you get is a dew point. Okay. So, these are some of the outputs which we try to get from psychrometric chart: dry bulb temperature, humidity ratio, saturation curves. So, this is dry bulb temperature is given, humidity ratio is given, then you have saturation curves. Then from here what do? Is we try to calculate the relative humidity lines, then wet bulb temperature lines, then enthalpy lines, which are very important. Then we try to calculate the specific volume line, then finally dew point temperature. For psychrometric processes of a chart is sensible heating and cooling. You can try to draw horizontal movement to the right or to the left. Right is heating, left is cooling. So, you can try to have this, and no change in the humidity ratio will happen. So, we will try to find out what is the sensible heating or cooling. So, the ratio humidification or dehumidification in the vertical line movement, upward adds moisture, downward removes moisture. So, you can try to have humidification and dehumidification. The temperature makes a no change. So, this is humidity. If you go up, if you go low, if you go this side, heating, cooling. So, that is also got from this chart. See, now it is a combination. You can do, if it is heating, you go this side it is cooling, and if you go this side it is heating. Now, you want to draw with only heating or with cooling. So, that is what is told here. So, cooling with the dehumidification. So, diagonal movement down to the left, the temperature and the humidity both decreases, often passes through a saturation line, which is where the condensation begins. Heating with humidity, this is cooling with dehumidification. Heating with humidification diagonally moves right, both temperature and humidity increases. So, this creates evaporative cooling, which is otherwise called as adiabatic saturation, movement along the constant wet bulb temperature or enthalpy lines. The temperature decreases, humidity increases, enthalpy remains constant. So, with this you can get all these datas. Why? Because we are trying, why this is nothing but air water vapor mixture is there. Now, I try to move this as ideal gas. Now, I have this. So, with this what do? Is I try to figure out every relationship. So, for that what do? I go for this psychrometric chart. So, this I will try to figure out. So, cooling with humidity, cooling with dehumidity, heating with humidity, evaporative cooling. So, what are psychrometric processes? Psychrometric processes describes how moist air is conditioned. Moist air is conditioned or altered for specific application like air conditioning, drying or ventilation, right. In various processes we do. Each process involves a change in one or more thermodynamic properties such as dry bulb temperature, humidity ratio, enthalpy and relative humidity. Every process has this: dry bulb temperature, humidity ratio, enthalpy and relative humidity. These processes are conveniently visualized and analyzed using this psychrometric charts, which helps determining energy requirements and equipment design we always try to do. We explore 5 major psychrometric processes: sensible heating, sensible cooling, humidification, dehumidification and adiabatic saturation, which is nothing but evaporative cooling. with the path on the chart and the governing equations, we can try to design the process. What is sensible heating? Which we have seen, right? Sensible heating, we always talk about sensible heating. In sensible heating, the dry bulb temperature of the air increases while the humidity ratio remains constant. No moisture is added or removed. That is sensible heating. The dry bulb temperature of air increases with humidity ratio remaining constant. This process is depicted as a horizontal line moving right to the psychrometric chart. So, assumption is no moisture exchange happens, cold air, heat coil, you get hot air. Pressure constant, only sensible heating is added, which is a heater used in winter days. In sensible heating, the dry bulb temperature of air increases while the humidity ratio remains constant on a cold winter day. So, which is derived by this equation m into mass flow rate, because mass flow rate is the air which is cold air which is coming up, and CPA is the specific heat of dry air, the temperature difference. This is used in space heating, heating ducts, preheating in HVAC. So, effect of adding sensible heating and removing sensible heating. So, this is heating, this is cooling. So, you have wet bulb temperature, dry bulb temperature, relative humidity, and now you know all the extractions, whatever you want you can do. Sensible cooling is you pass hot air and you get a cold air. So, this is inverse of heating, right. At air temperature drops with no change in the moisture content. Here also it is the same, with no moisture is added or removed. So, here it is cooling. The process follows a horizontal path to the left of the psychrometric chart. So, the equation is given as the same. Cooling is MA CPA T1 minus T2. Application is air cooler, ventilation system and dehumidification. Cooling with dehumidification. Typically in air condition, so dehumidification is water content has to be removed out. Here most moist air is cooled below its dew point, causing water vapor to condense. Both dry bulb temperature and humidity ratio decreases. This path is a downward slope line to the left, often ending to the saturation curve, which is the saturation curve is ending to the saturation curve. Latent heat removed from the during condensation adds to the cooling load. So, this is calculated by this way. So, that is why in your AC, when hot humid air from outside is coming, it cools and then you will have always a dehumidifier. So, that is why you see water coming out of your air condition. In a rainy season day, you can always see there will be all the ACs will have a duct through which the water comes out, is because of cooling with dehumidification. Humidification, steaming process or spraying process, adds moisture to the air. This I said on a winter day where heater is used. The increasing humidity ratio and sometimes temperature. On this chart, this process moves upward, often diagonal to the right. So, this is how you try to calculate the steam humidification, which is M steam is nothing but MA omega 2 minus omega 1. So, the spray humidification enthalpy remains nearly constant. The air cools slightly as water evaporates, sloping line towards WT, which is H1 is equal to H2. Application is it is used in greenhouse, air washers and textile manufacturing, steam or spraying. So, we use steam cleaning for utensils. So, that is called as air washers, right. Textile manufacturing also uses this. So, here what we do is we will have a cold air is passed, you will have a heating coil, then what we have is steam nozzles we have, then we have hot humid air is passed into. This is heating and humidification, which is cooling, dehumidification. This is humidification, heating and humidification. The last part is adiabatic cooling. So, in adiabatic evaporative cooling, it is a constant enthalpy process where water evaporates into the dry air, absorbing latent heat from the air. The equation is H1 is equal to H2, which is CPA, A times T1, adiabatic temperature. It is a constant enthalpy process where water evaporates into dry air. So, this is on a desert cooler, we always have this adiabatic evaporative cooling. So, what we do in desert cooling is you have a fan which rotates at a very high speed, then we have water filled. So, now when the fan rotates, the air is dry, this fan tried to evaporate water, and this evaporated water through the fan is pushed into the dry space. So, then you have an increase in water vapor in the system. So, it is a constant enthalpy process where evaporation into dry air is happening. So, the dry bulb temperature drops, humidity ratio increases, the wet bulb temperature stays constant, the equation is given like this. So, this is a function of in a desert cooler. So, I have given you all examples: desert cooler, how does it work? Then I have given you a air washer, how does it work? Then I have given you an air condition, how does it work? Then I have also given you air cooler, how does it work? So, now you can understand all these things: sensible cooling, cooling with dehumidification, cooling humidification, then drying with humidification, then evaporative humidification. So, this psychrometer, any instrument capable of measuring psychrometric state of air is called a psychrometer. It comprises of two thermometers with the bulb of one converted by the moist wig. For example, thermometer 1, thermometer 2, two thermometers with the bulb of one covered by the moist wig. So, that is what we see, wet bulb. The two sensing bulbs are separated and shaded from each other, so that the radiation heat transfer between the two becomes negligible. Sling psychrometer, widely used for the measurement where air velocity inside the room is very small. It consists of thermometer mounted side by side and fitted in a frame with a handle for whirling the device through air. Sling psychrometer, and this is another psychrometer chart. This requires the air circulation of this over a sensible bulb is obtained by whirling the psychrometer to this. Readings are made when both the thermometers show a steady state reading. So, there is another one which is called as aspirated. The thermometer remains stationary and a small fan, blower or a syringe moves the air across the thermometer bulb. So, you see here three different. So, first they say about the psychrometer is used, it has a wet bulb and dry bulb. So, in this we have a sling type and then we have a aspirated type. In a sling type, what we do is the air velocity inside the room is constant or it is very small. So, now you try to put both side by side and then with a handle you are whirling the device through air. So, the whirling speed is 300 RPM. You measure the reading at a steady state. Aspirated psychrometer, here you use a small fan to blow, fan, blower or a syringe moves the air across the thermometer bulb. The wigs made of cotton or cloth should be replaced frequently and most distilled water should be used for wetting. This type is otherwise called as DPT meter, hygrometer or it is called as Dumore electric hygrometer. This is nothing but aspirated psychrometer. So, in this chapter we saw property table and we saw the state about psychrometry of air, then psychrometry chart, how do you use the psychrometric chart and the characteristics of psychrometric process. Then finally, we saw what is psychrometer and what are the different types of psychrometers. So, it is nothing but a wet bulb and a dry bulb. So, friends, let us try to do some small experiments. So, you try to take maybe a small leaf, green leaf, keep it inside a oven. Set the temperature to T1, then to T2, then to T3, where T1 is lower, T3 is higher, and see what is the response of the shape, size and color happening to the leaf. The leaf should be little larger. So, keep a larger leaf in an oven and see what happens. Next, try to do the same experiment with T1, T2 and T3, wherein which you keep the leaf. The leaf should be covered by a cotton cloth. Same leaf covered by a cotton cloth. Now, you record it with time. What is the change of shape, size and color, right? So, here with a cloth which is covering and this, and then let us try to go to a cleaning station. You try to take a vessel which has oil coating in it, oil thin film. You try to remove this thin film only with cold water, then with steam. Then with steam and wash it for the same time. Now, you see what happens to this two cleaning and what is the effect of steam with respect to the output. This is the second experiment, experiment 1, experiment 2. The last experiment is try to take a hand kerchief and try to have 2 different days, day 1 which is a sunny day, day 2 which is a rainy day, and you try to partially, for example, up to here or up to here, or you can try to have 25% loading with water, 50% loading with water. Dry it on a day 1 which is sunny and dry it on a day 2 which is rainy, and try to plot the dryness with respect to time. When does it dry, how does it dry for 2 things. And now, with all these experiments, you will try to understand what is the influence of thermodynamics in real time use, wherein which the measurable parameters are going to be pressure and temperature. Right? Now, at various conditions, we are supposed to see how does it perform with different outputs. So, friends, when we do all these 3 experiments and go through this chapter once again, you will start appreciating why is this important. Now, these are all simple experiments. Now, these experiments have to be integrated into a system wherein which multiple processes happen. So, that gives you a better clarity of this chapter. So, these are the references which we have used for preparing the slides for this particular chapter, and thank you very much.